Okay, everything should be going okay. Hello, Professor T. How are you?
Good evening. How are you?
Good, good. Okay.
It's been a
Welcome,
week.
welcome to everyone tuning in to the live stream, and if you're watching this after the fact, hello, hello. So, bit of, well, main focus of today is going to be GCSEs. Hi, Waha. But I just have this initial A-level, I think actually further maths question because it has an art-cosh identity. So I'm going to go through this. If you are studying GCSEs, don't worry, we'll get into some GCSE revision after this. But I did want to go through this because someone brought this question up. And I wanted to make sure we're doing it properly because I feel like there's, you can think you understand how to do these questions, but not be following the right process, or you might be following the right process, and I just want to make sure we're doing that correctly, and that's really all that I want to do here. So the question is to take this definite integral from 1 to 2 of 1 over the square root of 25x squared take 16 dx, and we have this identity we want to make use of. This is in the formula booklet for A-level further maths, I think, or A-level maths, which says the integral of 1 over the root of x squared take 1 dx is equal to arc cosh x. Okay, so we have this expression in the question here of 25x squared take 16, and we want to somehow convert it into the square root of x squared take 1, such that we can use this identity, because then things will go much smoother. So the question is, can we do that? Is it possible? Well, let's just have a look at this expression. 25x squared take 16. Let's suppose that we substitute something in for x. Let's say x equals u on 5. So we're going to substitute u on 5 for x. Okay, now this is going to change the integral. The bounds are going to change, and we're going to be integrating in terms of u. That's fine, but let's see what happens. So I'm going to leave the interval off because we can recalculate it if we need to. But let's see what happens. So let's plug in u on 5 for x here. Would get the square root of 25 u on 5 all squared take 16. And then we also need to compute dx. So dx would equal 1/5 du. So then we substitute a 5th du for dx. Okay. And now notice here, what's happening in this expression? Well, we're going to square this u on 5, and now we're going to get 25 times u squared on 25. That gives us a u squared. How do you figure out the substitution? That is a good question. That's what I'm trying to get to right now. So this, basically I'm looking at this term here. I'm not saying this is the correct substitution yet. I'm just saying this is something you could try. So I'm looking at this term and thinking, well, how can I convert that to something, just one term squared without a number there? How do I get rid of that number, basically, is the question I'm asking. How do I get rid of 25? Well, I substitute something over 5 squared, right? Hopefully that makes sense. Because now what this turns into is the integral of 1 over the square root of u squared take 16. Okay? So now we have just this unknown squared as the first term under the square root. The next problem is we have a 16. We want to change that to 1. So how could we do that? Well, if instead of substituting u on 5 for x, I substitute 4u on 5, notice what happens. Let's change these terms here. So in this first set of brackets, we have 4u on 5, and this derivative would also change. So now it's 4 on 5 du, 4 on 5 du, 4 on 5 du. And so now when we square that, it's going to be 16u squared over 25. And here, this term would be 16u squared. Take 16. See that? Because I substituted 4u on 5 for x, I now have 16u squared take 16 under the square root. That's really nice because if I factor out a 16, I'm going to be left with u squared take 1 under the square root, which is what we wanted. So there's really, I wouldn't say there's a hard and fast rule as to how to figure out this substitution, but I think this is what you have to do here. It's probably not the only method, but it's I expect it's the method that they wanted you to use. Please correct me if I'm wrong. If you have a different method, then I'm happy to go through or hear that as well. Okay, so let's keep going. This is going to be 1 over the square root of 16 times u squared take 1. Square root of 16 is 4. And then this ends up being 4 on 5 over, multiplied by 1 over 4 the square root of u take 1, u squared take 1 du. And those 4's would cancel. And so now we have the identity we were looking for, right? This is the integral of 1 over u squared take 1, which we know is arc cosh u. Okay, hopefully that made sense. So let's say this is 1/5 arc cosh u. And because I left the bounds off there, I'm just going to substitute the expression for x back into this. So u, following from the substitution we made, u is equal to 5x on 4. So if we substitute that back in, we can say then that, do I have a bit more room here? No. Well, let me try to squeeze it in at the bottom. We can say that the integral of from 1 to 2 of all of this, because of all the work we just did, we can say that's 1/5 arc cosh 5x on 4 from 1 to 2. Now if you work that out, so you do arc cosh 10 on 4, take arc cosh 5 on 4, you should get the answer of, let me just double check, you should get approximately 0.175. Okay, so yeah, that would be the method I would suggest. Yeah, there you go. So that was a starter on A-level integration, and now we're going to get into some trig identities for GCSEs. I took the 25 out as a factor, then put the 1/5 on the outside of the integral to get the x squared. I like this way though. Okay, so if you take 25 out, I'm just curious how you're getting the 1. So if you take 25 out of that expression, you need the 1 on the end here, I think. Or how did you deal with that? I'm just curious. There's probably a way to do it that way. I mean, if you get this expression in the integral, it just makes life easier, I guess, is what I'm trying to say. Alright, okay, so let's move on to some trig identities. These were sent in by HA. This was for GCSE Further Mathematics, I believe. And hopefully he's with us. Okay, so, or he can always catch this after the fact as well. So this question says, prove the following identities. Part 1 says the tan of x multiplied by the square root of 1 take sine squared x is equivalent to sine x. And for this, we want to make use of the fact that tan x equals sine x on cosine x. And also, the other identity we want to make use of, which you learn about in GCSE Further Maths, I think, is that sine squared plus cosine squared x equals 1. Okay, so using these two identities, we want to see if we can take this expression on the left and find that it also equals sine x. The other thing I want to do with this this identity here, sine squared plus cosine squared x equals 1, is to notice that if we rearrange this, for example, we can say cosine squared x equals 1 take sine squared x. And likewise, you could say sine squared x equals 1 take cosine squared x. So for part I, maybe you can notice what we're going to do. I'm going to say, using the left-hand side, tan of x, well, let's write the thing out first. This is how you solve trig identities, by the way. You pick one side, and then you show that it is equal to the right-hand side. So here I'm going to substitute sine x on cosine x for tan x. And then I'm going to substitute cosine squared for 1 take sine squared under this square root. And then you notice if we have the square root of something squared, they cancel each other out. So this is just cosine x. So then we're left with sine x, which is the right-hand side. Pretty nice. Okay, part 2. 1 take cosine squared x over 1 take sine squared x is equivalent to tan squared x. Let's again work with the left-hand side. Remember we said sine squared x is equal to 1 take cosine squared x. So I'm going to, well, again, I'm going to write the whole thing out again and then make those substitutions. So 1 take cosine squared x is sine squared x. That's just a rearrangement of this identity, sometimes called the Pythagorean identity, or the trigonometric Pythagorean identity. Okay, so the top line here, we're going to say is sine squared x. On the bottom line, we've got cosine squared x, and this is equal to tan squared x, right? Because this is sine x on cosine x all squared. Okay, that was part 2. Part 3, let's rub out this first part here. Part 3. we've got 1 plus sine x, 1 take sine x, and this is the left-hand side. We were talking about the difference of two squares last week, I think, or the week before. So here, hopefully you notice that this looks like the difference of two squares. If you're not sure what I'm talking about, you can just expand these double brackets and you'll find you do get 1 take sine squared x. And again, this is this identity over here, which is equal to cosine squared. And there we have our right-hand side. So we say, I should have been writing this is equal to the right-hand side. And the final part, is we have this expression 2 sine cosine, 2 sine x cosine x over tan x. This is the left-hand side. We need to show that this is equal to 2 take 2 sine squared x. I would write tan x in terms of sine and cosine. One tip when you're given some trig identities, if you're given tan, for example, write everything in terms of sine and cosine, and that should make your life easier. So here, if we write tan in terms of sine and cosine, we have a fraction in the denominator, which, if you remember how to divide and multiply fractions, if you divide by a fraction, it's like multiplying by its inverse. So we can say this is 2 sine x cosine x multiplied by cosine x over sine x. Which, if you look at the denominator of that fraction, you notice it cancels with the sine x in the numerator. So here we're left with 2 times cosine x times cosine x. Another way to write that is 2 cosine squared x. And remember the identity for cosine squared x. That is 2 times 1 take sine squared x. Hopefully that's still showing on the screen. It should be. And if you expand those brackets, you get 2 take 2 sine squared x. Oops, didn't need that bracket there. Which is the right-hand side. Okay. So there you go, HA. I guess you're not in the live stream at the moment, but hopefully you watch this after the fact, and that is helpful. Alright, so that is some trig identities problems. Hello, Daniel. I didn't take A-level maths, but when I did chemistry at university, I had to take a math subsidiary module. Found people fear mathematics because it was badly taught to them in the past. Right. Oh, HA, welcome. No problem. Hopefully that was helpful. Okay, so now we're going to move on to, which question did you want to do next, Professor T? Or did you want to do?
Well, maybe we should do this one. I was thinking have we done one of these yet? So I think no. And so perhaps we should. It's one of those strange concepts which I love. It's called, technically, if you want to look to the highest level, it's called numerical methods. And it's the whole idea of how you're going to process numbers, almost like brute force. It's computer science in a lot of ways. How do you do it without calculus, the magical calculus, or other such things, and algebra? It's how a computer would think to process something, right? So it's very bare bones, and I like it for that method, and because it requires some brute force, you've got to put numbers in, there's processing, and then it's going to come out, and well, it's not quite there, so you're going to put it back in, and you're going to get closer and closer. That iteration process, it could take forever. It may not even work, but basically, there's a cost, isn't there? There's a time cost, there's a computational cost, electric cost. It's all very real life stuff. I love it.
I
So,
did want to
hmm,
just say that usually these iteration form questions are much more structured, so they'll tell you exactly the steps to take. This one is probably the only question I've seen where it just says, you know, uh, like you have to find the iterative formula and and go through the iterations yourself. Exactly what you're writing here. Yeah.
something like this, right? So this is exactly the structure, and as you get older and older, you'll get less and less structure. With less structure means more complexity, and we usually will have a show that, which we love. You know what though? Sometimes when we have show that, we get obsessed about the answer, and when we get obsessed about the answer, we lose sight of our own journey through the question. Um, Wait, hold on. I'm getting harassed by ScanGuard. I decided to change antivirus, and now they're harassing me by popping up and
Oh,
being annoying. It's like, well, you haven't got a right to do that. What the hell? Okay, let's get going. So you see this question here, and you might think, okay, um, what does it say? Can I go up to the top of the... There we go. I wasn't looking at the very top. It says use an iterative formula. So there's the clue on the topic to find the positive root of the equation. So you might think of other ways of finding the root. You might think, I got this. I can factorize this. Okay, well, maybe you can't. Maybe you've got 5 and 1. It's not very nice. You could probably put it through a calculator and find where the roots of the equation are. Something like that. Totally rough. Don't quote me on that diagram. And you could find using a number of different ways, but you're forced to do it with iterative methods, right? Iterative meaning one process at a time, one logical step that will learn from itself in a sense and get better and better as we go along. Iterations can be some of the most complex and intelligent systems out there, and a lot of life forms rely on iterations. So so to calculate things like computers. So how do we do this? So it's very repetitive in a sense. To solve anything, we're going to set the thing equal to 0 because we're trying to find when y equals 0. So we can put that aside and focus on just this. And remember, y equals 0 is where the roots are. That's what that's all about. And there's a theory here that goes that if we can get 1x alone, then it would be a lot easier as an equation. I mean, I could tell you the most obvious one. You might want to get this x alone, right? So let's go down that garden path for a second. If we keep that x on this side, and then we'll shove everything over to the other side, that means this is going to be positive, that's become negative. We've got this new type of question that says, okay, on the left-hand side, we've got a function that's y equals x. On the right-hand side, we've got another function, but I don't think it's made our life any easier. It's still a quadratic. But what is this new question? It's a statement that says, when is the graph... Should we use a line for this? Not there, it's there. When is the graph of y equals x, which is this one, and get that off and go back to drawing, equal to the graph on the left, which is a negative x squared that crosses at about 5. Should we say something like this? And we're asking a new thing now. We're not asking when is, I'll draw it again up here. When are these graph going to cross the x-axis down here with the roots. We're now asking, when does the y equals x cross with this new quadratic that we've monstrously created? Which is arguably a more difficult question than before. And it's good to pursue this for a second to see the method and to see where it might go wrong, because this is only one possible way of getting an x on its own. If you're in the exam, as we said before, it's possible that the x, they'll tell you what to get alone, right? The x that you're supposed to be getting alone. In the case that it was this, and we'll find out whether it was or not in a minute, because this rearrangement may not work. The x that's on its own would represent the next possible guess for us. In other words, n plus 1. N representing the current x and n plus 1 representing the next. So where's the current x? It's over here. It's in the function that we still have. So we call the x's over on the right the xn. And typically, this will have some sort of start point. Visually, the start point would be a value of the x-axis here. So it could be something like there. It could be at 1, for example. And we'd put that into the function that's curvy on the right-hand side. That's this bit. And we would get a y value. So I believe if we do 1 this time, it's going to be 5 take away 1 squared. So that's going to be 4. And 4 is going to be our next guess that goes into the equation. But of course, if we put 4 into this equation, we get something dreadful. It's all the way over here, you see, 4. So it's going to travel along, if you want to draw a visual, to about there. And going to come down to be 4, our next one. But if we put that into the equation, we're going to be going down here. Something I haven't really drawn. But as you can see numerically, putting 4 into here, we'd have 5 take away 4 squared, which is negative 11. So when I look at this journey overall numerically now rather than visually, and we're going to see something rather quickly. Now, calculators at the ready, everyone. These sort of questions, you will need a calculator. We'll do the full-on method here so that we get it perfect every time. Typically 3 columns, but maybe just 1. We're going to have to decide on a value of x that we're going to start with. And for interests, for experiment's sake, you can do your own value of x. I'm going to start with x equals 1. This is the x naught, the initial one. You can start with a negative or a very big positive. I wonder if that will yield a better result, because there are 2 variables here. 1, the rearrangement, and 2, the start point. These can all make a big difference to our success. So if we're going to start with 1, as we've already done, our calculation will go in the middle. Let's just keep it nice and neat. That's all it is. And so we have our next, or the output of the original is going to be 5 take away 1 squared, so we've got 4. We've sorted that. So our next input is going to be that 4. You see, what comes out is our next best guess. That's then going to become 1 minus 4 squared. And I think you can see where this is going rather quickly. Negative 11. And now we've got something rather hideous here. Now, this is the time where you don't want to do this. You don't want to do this in the sense in your head too long. We're going to start making this iterative. So if you have this on your calculator, which is already like your answer from your previous one, we're then going to put that as the working out like this, right? Is this question GCSE level? Yeah, I'm pretty sure I've taught this to GCSE. It gets harder at A level. They started these new things with a new syllabus. Make your life harder, because it was too easy, wasn't it? So if we got 11 in the calculator now, press equals, that's now our answer. We'll do 5 subtract answer squared, and we're very quickly going to get our next values of x, which I then don't need to do the calculation for because I'm using my technology. Casio FX 991, by the way, if anyone's interested. Champion amongst calculators. This is getting rather large, okay? 13, if you've been following along and doing this yourself, at this point, you can hit the equals button just 3 more times, and you've already got a number which is 16 digits large. It's something what we call divergent. Okay, that doesn't mean that our whole method has failed. It just means that either this rearrangement here or this particular start point is not a good one. And I've actually experimented with this start point just very quickly while Maths Explained was doing the other question. And I'm going to tell you, it's not a very nice story. No matter where you pick, it's always going to diverge in many different ways, some quicker than others. I'm going to blame it on the bad rearrangement here. So hopefully, while you've been watching me do the method here, you've had to think about another way of rearranging this equation. So how else can you get this an x on its own? I've already gone for this one, so it's going to have to be something to do with that, right? So let's begin with x squared. Leave it alone, and then 5 subtract x. Well, the only logical step left. You may have seen questions like this before. They're like the square root. Throws you off, doesn't it? If we want to look at this one visually, I can definitely draw this. You must be thinking, what on earth does that look like? Well, what we've got is, as I said before, on the left-hand side, y equals x. So that's no problem. We can draw that. That's going to be a straight line. And we're pretty confident. What is this one, though? Well, it's a rearrangement of this, technically. And then what would this be if we made it negative? That would be a reflection in the y-axis, if you know your transformations. And then a 5 is a shift. Okay, so you plus 5, so you think, oh, well, that'd be nice to go that way. But overall, this graph looks something like this. I guess what you really want is, it's only a rough to look at, okay? What you really want is to plot this in something like Desmos or GeoGebra. And you can see that really, really neatly. And you can see that this graph and this graph cross right there. And if we go ahead and try and solve this one iteratively, it will be like finding where they cross over here. But this is the key. Finding where these two cross is the same as finding the original question, you know, the roots of the original question. The rearrangement yields the same numbers, but we're hoping that the rearrangement is an easier thing to do. That's the whole point of it, really. So we've got our visual. Let's do our method. And if you're working ahead, it's fairly quick to do. Question here, we leave ourselves with the option of where to start. I'm just going to start with 1 again. I don't know any better way to start, but, you know, sometimes they'll give you it. And we're going to then have the square root of 5 minus 1, which we know is square root of 42. Okay, I like it better already. So our output is 2, and our next input is going to be there. You can, I'm going to do one more. You can at this stage go straight to the answer button, but 2's going in now. So that's going to be the square root of 3. But now we're gonna go to decimals. So for x2, our calculation is going to be 5 minus answer, and we're going to keep pressing that. So join me on the journey, everybody. With your calculator, you're going to type square root 3 and press equals. That's now stored as the answer. Then we're going to go square root 5 minus answer, and all we have to do now is keep pressing equals. Make sure you do one at a time though, and write it down as we go. So my next, I'm just going to bear in mind how many decimal places we want right now. I don't need to go crazy because I know that I'm definitely nowhere near it. So I'm just going to do a couple of decimal places. Going back to the question, we need it correct to 5. That means that we're going to have to find this answer so that it doesn't change at 5 decimal places twice in a row. You could go pretty crazy. In fact, I don't really like writing X all the time either. That's bothering me. Let's keep pressing it and we'll just see where we're at. Hopefully it won't get too tedious. 6, 6, 8, 7. If I cover it by doing an extra 2, then let's have 79257 What I find is a really good thing to do when you've got your calculator already in this mode is to keep pressing the equals sign really fast, and look what happens to the number. It just slowly doesn't change at all. There'll be part of the number that stays the same. And as I write these, you can already see that there's a part of the number that's not changing every single time. 1.79125. So we're getting a lot closer now. There's a 1.79. This is going to be my last one. There's a point we will reach. But you can see now that if we rounded this, it wouldn't be quite the same. But let's say we were going for 4 decimal places. If we rounded that to 4 decimal places, that would both round to 1.7913. And therefore, we can stop. That's it to 4 decimal places. And as I said, you keep pressing equals, and eventually the number won't even change when you press equals. And you'll have found it to potentially 9 decimal places. Yeah, that's right. Newton-Raphson we learn at an A level, which is using calculus. So we find the derivative of the function and put it into some form, and the interval bisection method, which is a theory saying that if we cut it halfway and then evaluate it, if it's more than or less than 0, then that tells us about whether we're to the left or the right. And we could just keep halving the interval that's closest. Anyway, that is something for another day and that we don't need to know, but this is certainly a challenging one at GCSE because it doesn't tell us we know what to do. We've got to kind of recognize it and go our own way. And it's very lucky that this one, using 1 at the beginning, converged. Let's use that key. Let's write that keyword here. Converges. What that means is you could see the number is slowly getting towards a particular number, not moving away, slowly chipping away and getting rid of a smaller and smaller amount until we settle on a solid 1.79. Whereas the other one over on the left just got bigger, massive, didn't go anywhere. You can see that in a spider, what they call it, a cobweb diagram, but that's nothing we're going to do here today. That's much better animated anyway. Well, that's it for that question, I'd say. Oh yeah, floods. That's exactly what I was just saying. Yeah, cobweb graph. As you can see, let's use a different color. What's contrasts? Blue, perhaps. If we started with a point here and we went into the graph like this, that would be our next guess, right? And that means we go to here and then we go down, and this is our next value. Then we go up to the function, and that's our next value. So we go across to there. Well, this isn't the best diagram. If it was drawn accurately, what you would see is it go around and around like this, which technically is our cobweb, right? And it will slowly get closer and closer to that point. If it didn't, you would see it go up to the diagram. I can't do it on this one because it's not an example of where it would do that, but I'd do it roughly. It would do this. Just diverge away. It just couldn't go anywhere. It just gets bigger and bigger, and it doesn't settle on that point. That point is what we're aiming for. That's the end of that question.
I think it's worth just talking about what the skills needed here. So let's say, like, I can't see this question coming up in a GCSE exam anytime soon. I think they're still going to stick to the structured questions, the way they do this. But let's say in the future that this does come up in an exam. Let's talk about the skills. So you would firstly have to try some different formulas. Then you'd have to recognize which ones diverge and which ones converge. And as soon as you find the one that converges, then you will get your answer, um, which is quite a lot, really.
But if you're practicing these questions, like to notice that it's iterative from the beginning, it's a matter of memory about what you'd be expecting. And a lot of that then would be confidence to say, well, I'm expecting this.
Yeah,
Let's push on with this.
yeah, it's yeah. I think that it's certainly something they could try. As I said, I don't think it will come up in for example, this year's exams, but it's a possibility. Um,
Famous last words, eh?
yeah, and the other thing was, why are we only getting one root? Oh, positive root. Yeah, yeah. Sorry, I missed the positive root. So the other one would be a negative root. Okay. So
Oh
would
yeah,
there
for sure.
be?
We've got this one over here that we've focused on.
So then, if we started
And
at maybe at -1, we'd find the negative root, possibly.
sometimes it depends on where you start. So if you're close to the particular root, it can hone in because you're close to it. And if you're looking for the negative, you might do that. But if you just observe our rearrangement, these graphs only meet at one point. They only meet at the positive. The other rearrangement was like this, and it did have 2 points of intersection, but
Mm,
it was a convergent rearrange. It was a divergent rearrangement, so it's
mm.
not going to yield anything. There are definitely limits to this method,
Well,
right?
uh, does it? I mean, if you pick the correct starting point, doesn't it sometimes? No. Well,
Well, I've
what if we
actually
tried
for this
something
question,
less than zero, less than
yeah,
one, or
I
between?
tried mine earlier. I tried -4, -1, 1, and 5, and all of those diverged in different ways, but very quickly.
What if we tried something between 0 and 1, like a half? What would happen? So,
Yeah, I mean, go for it. I mean, it's possible. Really depends on the start point, but it was I wanted to just I guess
yeah, I
express
guess I
that
wouldn't
if you
like.
rearrange it differently, your life can be a lot
Yeah,
easier.
good question. Yeah, that was great.
Could you
Okay,
like 0.5 then? I'll try 0.5. Let's see how that goes. I'm
sure.
always hopeful, ever the optimist. Right,
But
so we've
I
got 5 subtract answer squared because obviously if it's a fraction, right, that could get smaller and smaller. That's a good call. All right, we've got 4.75 minus 17.56
no, yeah, it's not gonna work.
minus 303 minus 100,000. No, we're killing it here. I think the point is that if it's 5 subtract that number and it's squared, that's going to get a lot bigger than the 5 itself, and maybe that's why.
Yeah. Yes, yes, yes. So, I wonder if there is a. How would you find the negative root? Maybe a different. Maybe that's an exercise for the viewers. Okay.
I assume they've put it there because there's only one, you can only find the positive
Oh, right.
that
Okay. Interesting.
using that methodology anyway.
So we have a couple of options here. We have inequalities. We have proof. We also had an interest rates problem. Are there any preferences? Uh,
Is there a way to know which form of the equation will diverge or converge beforehand? Yes. If you're very good with graph shapes, you can tell by the shape of the graph. If you do enough cobweb graphs, you can see that certain shapes are going to diverge away from because the methodology is the x value goes straight up to the function and then across to y equals x, then down to the x-axis and back up to the function, then across to y equals x, as a conversion that the y value that just came out is now turned into the x value. And then if you observe that you've got an incoming gradient that's decreasing versus one that's increasing or exponential, you'll notice certain, I like to call them tunnels. And I drew this sort of tunnel here. It's impossible for that to happen here because after you hit the graph, you have to go towards y equals x. And so it's not going to send you up that tunnel. But certainly, if it was going the other way, you might end up going up a tunnel like this. So, yes, through a little bit of wisdom of how it's drawn, you could probably do that. And I'm sure there's some more advanced analysis. But really, it's not too bad at this level. The equations aren't awful. But I suppose you're wondering why you even bother doing it at all. And the answer is that some equations you just cannot solve any other way. Some equations are god awful. If you want to use calculus or some algebraic methods and trigonometry, it's not possible. So sometimes it can be very efficient to just brute force it.
Alright, let's jump into a proof question then. So this question says, prove that 3x plus 1 all squared take 3x take 1 all squared is a multiple of 4 for all positive integers values of x. To start off these questions, if you're intimidated at all by any of this language here, I would suggest just following your intuition. What do you think you should do first here? If you see a binomial squared or an expression like this, what do you feel like doing with this expression? Hopefully you feel like expanding the brackets and simplifying like terms and seeing what you get. So I would suggest just going with that. So let's expand these brackets. 3x plus 1 all squared is 9x squared plus 6x plus 1. And then we have subtract 3x take 1 all squared, that's 9x take 6x plus 1. Now let's combine like terms. I said 9x, that should be 9x squared. What's going to cancel? 9x squared, take 9x squared, 6x. Yeah, that's a subtract, but then we have a negative 6x. That's going to become a plus. That's going to become a plus 12x. Then we have a 1 take 1, and they cancel out as well. 1 subtract 1, they are going to cancel as well. And so we're left with 12x, which is thankfully a multiple of 4. So if you really want to rub it in, you can write this as 4 times 3x, which is clearly a multiple of 4.
Not going to lie, I don't even think that's rubbing it in. I think that literally is required.
Yeah, I mean, you can never be too obvious in your exam, in your maths questions. I kind of used to dislike that in my mathematics classes when you're asked for an answer and I would write the answer down and I think, well, that's obviously fine, and then the maths teacher goes, well, you've just written 12x. What do you mean? You haven't explained it at all. And I go, well, obviously 12x is a multiple of 4, but I think sometimes what's going on in your mind is not obvious to someone reading your work, so spelling it out is always a good idea. All right.
Sometimes the 1 plus 1 is in my mind. The fact that they took a whole book to prove that 1 plus 1 is 1, it kind of takes it to the next level, doesn't it?
I mean, you've got to, so a mathematical proof is about, it's like, what does it achieve, as well as, Marcus de Soto is a mathematics author, and he describes what a mathematical proof is beautifully. But I can't remember his exact words. But he describes it as like not just a piece of technical work. It's like it's got to be beautiful as well. And so that proof, I think you could say, well, is it beautiful? What does it achieve? Does anyone ever refer to it as something, groundbreaking? I'm not sure, but
That's a kind of it's kind of sad, isn't it?
I mean, I think I
It has to be groundbreaking just because.
is it so do we say 1 plus 1 equals 2 because they proved that, or do we say 1 plus 1 equals 2 because if I pick up two apples, I have two apples? If I pick up an apple in my left hand and an apple in my right hand, I have two apples. I think you could probably prove in 300 pages 1 plus 1 does not equal 2 somehow. Uh, you know,
It's all condition based.
I think we just that's an axiom almost of it's like if we say if 1 plus 1 equals 2, then we can accept these other things. And we can also say 1 plus 1 equals 3 sometimes, and then we get synergy. And I don't think
I think because they took
writing
360 pages, it was 359 pages just to prove something like the arithmetical addition is even a thing.
sure.
That's what they did. They took so long to do everything else. Yeah.
Okay, yeah, maybe I don't know. I mean, for maybe in 100 years, that's going to be like fundamental to what we understand about mathematics. I don't know.
Let's go.
Okay, so should we jump into these ones? There's also an interest rates problem. This will probably be the last set of problems.
If it's the last, it really depends on the audience.
Poultry.
This
2 beans
feels a
plus
little
two
bit
beans equals some
basic.
beans. So we're doing the interest rates problem.
Yeah, go on. I feel like it's a little bit different.
All right. Okay. I'll do part A, and you can finish off. Okay. Reverse interest. Sheila invests £2,000 in a savings account for 3 years. The account pays compound interest at an annual rate of 2.5% for the first year, X% for the second year, and X% for the third year. There is a total amount of £2,124 and 46 pence in the saving account at the end of 3 years. Work out the rate of interest in the second year. All right. So we're given the interest rate for the first year. And I think it's probably necessary to work out how much we have after that first year. Blackadder. Okay. I should have recognized Baldrick. Yeah, I'm not up to date on my Blackadder references. So, after the first year, let's work that out. Well, we're going to use a multiplier here, percentage multiplier. So I'm going to say after the first year, we have the original amount, 2,000. And when we increase something by 2.5%, we multiply it by 1.025. Okay? So this is, 100% plus 2.5%. This would be the multiplier you get. And this is going to give us, I did these calculations earlier, that gives us £2,050 after the first year. So then we need to create an equation relating the amount after the first year to the total amount at the end of the 3 years. So we start with, after the first year, we start with £2,050. Then we multiply by what? We multiply by, let's call it 1 plus x. Okay? So notice when we multiply by when we increase by 2.5%, we do 1 plus 0.025. That's our multiplier. Here we're increasing by x%, so we're doing 1 plus x. And we do that for 2 years, so we're going to square that. Okay, we multiply by 1 plus x, and then we would multiply by 1 plus x again. So that repeated multiplication we can represent as a square. And at the end of those 2 years, we get 2,124.46 pounds. Okay, now we have an equation we can solve for x. Alright, I'm going to divide by 2050 on both sides, and then square both, take the square root of both sides. So I get 1 plus x equal to the square root of 2,124.46 over 2050. And then you need, this is a calculator question, by the way. I think that's a beautiful calculator. You're never going to get this type of question where you're taking this problem without a calculator. If you do that calculation, plug that in, you don't get an exact value, so put that square root into your calculator and subtract 1 for x. You get 0.017999 or something close to that, which I rounded off to 1.8%. So to answer the question, the rate of interest in the second year I'm saying is 1.8%. Okie doke. So a nice reverse interest rates problem there.
Nice. Although I just read the second part and it's nothing to do with this one,
Yeah.
sadly.
Yeah, so maybe we don't need to. Okay, so does anyone else have any other questions? Bit of a shorter stream today. Yeah, I don't know why. I've never been like a stickler for details in that way of proving, because it's kind of the way I think about it is it's turtles all the way down in a way. You can keep going, like, if you want to prove 1 plus 1 equals 2, if you want to prove that definitively, well, there's what's the next step is to prove 1 equals 1, right? Or, 1, I don't even know, I'm trying to think in more granular. But you can always, and that relates to Gödel's theorem, right? There's always proofs that you can't prove, or statements you can't prove within the system that you're working in.
Yeah, I'm going to admit I've not fully got to grips with that statement. I've heard of it, so I'm saying I know where you're coming from, but I'm not going to believe it blindly. I'm going to study it one time.
Do you have time to go over binomial expansion question really quickly? Sure. If you post it in the Discord. Gödel's theorem. Well, it's very specific. I studied it a while ago. It was explained really well in a book I read. And I don't remember all the details, but basically he just shows, well, you can create this system. It's kind of like those paradoxes, like, if you have a card and on one side it says the other side of this card is blank, and then you flip it over and it says the same thing. Or or what's that other? It's Berry's paradox, I think it's called, where you can let me look that up. Oops, wrong one. Why is it doing that? Let me look that up. Yeah, Berry's paradox. The smallest positive integer not definable in under 60 letters is a phrase with 57 letters.
Yeah.
If that makes sense. So imagine that you can define a number by describing how many letters you use to describe that number. So the smallest positive integer not definable in under 60 letters. So how many letters you use to describe that number. And then you've just described it with 57 letters. So it's like, kind of like, it's related to paradoxes like that.
Wow. Kind of a minefield, really, isn't it?
Yeah. Okay. So let's delete this. Okay, find the constant term in the expansion. Find the constant term in the expansion. In the expansion of. Okie doke. We did a question like this last time, right?
Do we? Or we jump to a specific term in the expansion?
No, but we did the whole expansion.
Okay.
Constant term. Why would there be a constant term? Oh, that would be where 2x cancels with the x.
Yeah.
So that would have to be okay. So let's just revisit the, just so we're not pulling things from left field. The binomial theorem says that if we expand a binomial to the power of n, this is going to be n choose, so a to the n plus n choose 1, or just n, a to the n take 1b, plus n choose 2, a to the n take 2b squared, and so on, all the way up to b to the n. So basically what I'm thinking about is what term here would we have such that we have 3 on x to the same power, I guess, as 2 to the x. So that would be where they're both to the power of 5, I'm guessing.
What, so they cancel?
That's what I'm thinking. So,
well, as you go up, isn't the B gonna keep going? Doesn't it start high? Or no, it's A that starts high, right?
yeah. So
So
well,
at
let's
the
go through a
very end,
few.
it's
So the
going to be
first term
zero,
is going
isn't
to
it?
be 2x to the 10, yada yada yada. Let's say we got to the fifth term. that would be 2x, 10 choose 5. 1, 2, 3, or 6. 6. No, 10 choose 5. 2x to the 5. Then 3 on x to the 5. And that would be the fifth term, right?
Yeah, yeah.
So let's say, and I think this would be the only constant term, because the rest would have x's in them. So let's focus on this one. 10 choose 5, I don't know.
I gotcha. 10 choose 5. 252.
Alright. So we're going to take this expression, pull it out. 252. Is that what you said?
252, yeah.
It's going to be 252 times 32x to the 5, 3 to the 5, so 81, 3, 2, 43?
What, 3 to the 5?
Yeah.
243, yeah.
How do I know it was the fifth term? Okay, so if you understand how to do a binomial expansion, we were looking at these terms here. These exponents, sorry. We were looking at these exponents, and looking at these terms in this binomial, 2x and 3 on x, the way you're going to get a constant term is if those x's cancel out. So how are you going to get those x's to cancel out? It's if these exponents are the same. Because then what you can do is say this is 32x to the 5 multiplied by 3 to the 5, which is 243, over x to the 5. And what happens there is then those x to the 5s cancel out. So you're just left with a constant. Alright, so the focus there was on the exponents and these terms in the binomial. Because we have an x in the denominator, we're going to want those to cancel out. Awesome. So then we're just left with this multiplication. Which doesn't look too nice.
This is huge. 1959552.
Uh, 25 squared, 6.
You might be better off with 252 rather than. Oh, yeah,
Is that
fair
too
enough.
many zeros? 3. No, it's not, is it?
No, it's 2 zeros.
Is it? Oh, yeah. 250. Seven, 1500.
1750, isn't it?
Huh? Is it 17?
It has to be more than 1500 because 7 times 2 is 14.
Yeah, why did I say um
Because not what people realize is it's quite late.
7? I was thinking 7 times 2.5. Yeah, it's 5. Oh no,
That's
no, plus
good.
3.5. 14, 7, yeah, 1750. Yeah, I forgot the plus 350 for some reason. Uh, that's not,
That's right.
that's
There you
not,
go. Well,
that's,
that's actually a lot nicer to work with.
is it plus 5? Oh, so that's 6,300. Take, uh, I'm just going to leave it like that. 3,000 take 1750.
61236 if you want a quick speed up. I know you're doing the battle. I mean, I know you're going to get there, even if it's column methods, but
Two,
that's your
so,
one. And then you need to multiply that by 32.
uh, right. So 61236 times 32.
Not bad.
Uh,
Times 10, times 3, and times 2. It's not
times
bad.
10 times 3. 18. Uh, okay, so multiplying this by 3, that's not too bad, is it?
Whichever way first. Yeah, maybe 3 first. Save 10 to the end.
Times 3. 7. 183,708.
I'm going to double check that because it's worth it. That's correct.
Uh, wait, 1.
Yep. 4, 3, 1, 6, 7, 1, 2, 3.
367,416
Correct.
times 10. So add a 0. 3,674,160.
I feel like that's unreasonable.
Well, is it correct?
No.
It's not.
Well, I don't know what you're missing. If you times it by 3 and then times by 2, that's times by 6. And then you times it by 10.
I'm not an
It's
order of magnitude off, so it is in the millions.
Oh, yeah, it's 1.9 million.
Yeah. Uh,
Because what you've multiplied it by is 60, right? 3 times 2 is 6, times 10 is 6t. But we wanted
oh,
32, so it's
oh,
roughly double.
3 times. So I did multiply by 6. Why did I do multiply by 6?
I don't know.
Doesn't
You could
make
have
any
done
sense.
2 by 4 by 4.
Yeah, 8 times 4. It's like double it. It's double it 5 times. Yeah, anyway, okay. Final
I'm going back.
answer. I messed up.
Final
For
answer,
some
just so
reason, you
for the
said
record.
3 times 10 times 2, and I just thought, yeah. So final answer 1,959,552.
Bullseye. There you go.
This was a question on one of my tests, and I was super confused. Okay, well, hopefully that helped. No, don't worry about the numerical business at the end. That doesn't matter, but the process to get there was the important part.
Did we do question five? Did you do question five earlier?
It is possible to do question 5 from the trig identities. I've done a few steps. Okay, so that was another bit from these questions here.
I see. So it's cos squared x tan squared x. You've got to write it in terms of sine x.
Do you want to do that one?
Well, I can have a go. All we're doing is trying to get to some. How do we clear the page? There we go. From writing. Can I get rid of all this?
Yep.
Yeah, you don't mind. Okay. All we're gonna have to do is try our best to get somewhere. Now, if I remember rightly, the only things that you guys know at your level is this. At A level, you get a little bit more, but technically everything comes from these, and you can derive a number of other things from it. But let's just say we'll bear that in mind. Right, what we're looking at, cos squared. Oh, it's going to be a bit of a habit to get back into putting an x. Tan squared x. Just so you know, at university we don't do the x really. We just write it like this. So if that's confusing, just let me know. Um, so we need to write this in terms of sine x. Obviously, the problem is sometimes if we do replace one of these, then they could end up introducing something different that we didn't want before. Like, for example, tan squared. I don't know if you realize, but you can make it tan. Let me put x for you. You can make it tan squared x and then this right hand side becomes sine squared x, cos squared x, like this, right? So that's also possible. I don't want to go too much. Like I don't know what is in the specification for further maths GCSE. Maybe you can confirm in the chat whether you've seen this before. I don't know. Everyone, you guys are all doing great life. If good, take care, have fun. Thank you, Morphos. You take care too. Cos squared tan x. So let's just try a few things to just show it in here. So let's just say we change this sine squared to be over cos squared. Oh, that's a shame. I just got and did it straight away, but that's fine. I wanted to demonstrate how you can just try something and it may not work out. Um, but I think that's the key then. Without me realizing it, I've stumbled upon a tool that was the key that you may not have done before. They cancel out, and then you've got sine squared x. I was just having a look at the cos squared, right? You could go down this whole road where you've got sine squared like this, and then you get in a whole world of bother because, well, you think, well done, I've got closer with sine squared, and then the only thing I can do with tan squared is make it sine over cosine, and then of course, oh, well, I got rid of tan, but I've introduced cosine now, and it could go on forever. That just writing in terms. So really, if you're going to switch out cosine to something sine, you're going to have the equation that switches the two, something like that. And if that's not the case, then look for cancelling. Change cos squared x to 1 minus 2 squared. Yeah. And multiplied sine squared over cos squared. Yeah, so what did you do there then? Oh, so you put that in there and was like, okay,
He was
sine.
just saying he did exactly what you were talking about. Yeah.
Oh, I thought this was the order.
No, no.
Oh,
Just
okay, cool.
exactly what
Did
you were.
exactly what I did. I accidentally did that one. I do apologize. I do sometimes try to build up, but it's a demonstration that you don't always know what's going to happen. You just keep trying stuff and remain confident. Currently, my screen is connecting, so I'll be
Uh,
back with you in a minute. Reset myself. What's the other question?
Tan x cosine squared x.
Tan x. Is that squared or cubed? That's cubed.
Oh, sorry, I didn't see the cube.
Well, I don't know what, as I said, I don't know what you've done in the course, but I assume that this is something that you're not used to seeing, and it's not something we can work with. You don't have an identity straight away. So I assume you want to think of this as more of a tan cosine squared sort of business that we're hoping that one of these cancel at some point. It looks to me it's fairly similar to this one up here. Um, so what we can do is, I suppose, play around with it. We know that tan is going to go to sine over cosine, and therefore this would cancel and leave us with cosine squared, which in turn we know is 1 minus sine squared. And we can get away with that, I think. It's only in terms of sine x, and that's cheating, isn't it? Sine, I'll put an x. Would you be happy with that? Maths explained. Do you see any other way?
Yeah, so, but the full expression would be what?
We just have to write it in
But you
terms
still
of
have,
sine squared, right?
you still
Oh, you're
have,
to do this whole thing. So I'd end up with cos cubed is like this, and then that cancels with that. Oh yeah. What's happened is the cos squared is in times of sine, yeah, and then we're going to multiply the sine in. Phew. Um, Sine x, and then sine cubed x.
yeah, I think that would be fine. It's all in
Doesn't say
terms of
about like
sine.
expand it fully, does it?
No, it just says in terms of sine, so I think that's fine.
Do we need any other? Let's get rid of that now. And there's one more, right?
One
Not to
more.
hog the whole show. I mean, if you're up for doing one, you just jump in, but I'm happy to do it.
Cos x multiplied by 2 cos x, take 3 tan x.
Cos x, let me have a look. Cos 2 cosine x minus 3 tan x. Oh, I'm getting some.
That's the one.
I think this one's okay. Did you want to take it or not?
Sure.
Go for it.
So, well, we could expand the brackets. I guess that's what we'll do. So if we
Probably the best, isn't it?
expand these brackets, we're going to get 2 cosine squared x. And then I'm going to write the tan in terms of sine and cosine. So this is 3 sine over cosine multiplied by cosine. Then we have the cosines here cancelling out. And I guess we just write the cosine squared in terms of sine
Yeah,
using
like what we got back there, yeah. And it's
this
almost like the
identity here.
previous question helps us there.
So this comes from our Pythagorean identity that we talked about earlier. And you could expand those brackets out as well if you like. No idea if it's necessary. I guess you could even write it as in terms of like a quadratic. So the squared term first, then the middle term, then the constant.
2 and 1. I think no, maybe I don't know. I can't tell right now if that's solvable.
2, 3, and 2.
So it'd be negative 2y minus 3y plus 2. I don't know. I mean, if it
4,
wasn't for that
4 and
2 at
1.
the front,
Should be.
b squared. So we've got 9 minus 4 times minus 2 times 2. Yeah, should be. Got a positive number there. 25. It should be actually quite nice. Yeah, it's totally solvable. I don't think that's in further math though.
GCSE solving trig quadrant. That Don't they? They do solving. I mean, there were some questions there about solving
They
trig
solve
equations.
quadratics, but I don't know if they have to recognize them inside other things.
All right.
Like you can appreciate you've got an x to the power of 4 plus 2x squared plus 10, and then you say y equals x squared, and then you define y squared plus 2y plus 10, and
Mm.
solve for this, and then substitute back into this. I don't think they do that at GCSE. I could be wrong.
Mm. All right. Thank you all for joining. I hope that was useful to you. Should be back next week, Professor T.
Every evidence to the positive.
Cool. All right. So it should be next week, either Tuesday or Thursday, and we'll see you then. Thank you, HA. No problem. All right. Catch you guys later. Bye.